Okay, 2.62 is sort of just the exact same problem as 2.61, with the only exception being that your potential is no longer zero. It's instead this sinusoid term. And this doesn't actually really change the way we solve this problem. The method that we use is sort of the exact same. The one big difference is that it makes implementing the code for this somewhat harder. So because of that, I'm only going to solve this up to the point where that code that's more difficult is taken care of, because once that's done, everything else is literally just copying the process of 2.61, and since I've already done 2.61, I don't really feel that it's worth my time to redo it again, just with different numbers. But you will see what I mean when we actually get there. So we have this non-zero potential, so because of that, our new Schrodinger equation is going to be negative h bar squared over 2m times the second derivative of psi with respect to x squared plus 500 times h bar squared divided by 2ma squared. And now this is multiplied by sine of pi times x divided by a multiplied by psi of x. And this is equal to our energy multiplied by psi. And then we have our boundary conditions, which is that psi of 0 is equal to 0 and psi of a is equal to 0. So let's use the method from 2.61 and substitute the second derivative with our interval notation. So negative h bar squared divided by 2m, and we're going to replace d2 psi by dx squared by psi j plus 1 minus 2 psi j plus psi j minus 1. And then this is divided by delta x squared. And then this is added with 500 times h bar squared over 2ma squared times sine of pi xj divided by a times sine times psi of xj, and this is equal to e times psi of xj. So immediately, one of the problems that we encounter here is note that sort of xj appears as a variable in this sinusoid. And this is going to cause an issue because remember, the whole point of doing this is so that we can create a matrix equation and solve sort of the eigenvalues for E. So because of that, E is actually our variable of interest. If you try to solve, if you set up your matrix without sort of taking care of this, what's going to happen is that your xj term is going to sort of appear as a variable. And because of that, it's going to prevent you from actually solving the energy equation numerically. You're not going to be able to find E in terms of numbers. You're going to find E in terms of some numbers multiplied by xj, because xj is a variable that is still present in this equation. So our first task is actually to get rid of xj. And we can actually get rid of it very easily because we can recognize that, assuming that we're splitting our interval into even spaces, right? xj can just be rewritten as j times delta x, where, remember, delta x is the space of each individual interval, so the value of x at the jth split is just going to be j number of evenly spaced intervals. So xj can just be rewritten as j times delta x. Next, if we then make the substitution that we did back in 2.61, which is that delta x can be rewritten as a over n plus 1, then in this case, our equation is then going to get rewritten as n plus 1 squared times h bar squared divided by 2ma squared, and then multiplied by negative psi of j plus 1 plus 2 plus 500 over n plus 1 squared times sine of j times pi divided by n plus 1 multiplied by psi j minus psi j minus 1, and this whole thing is then equal to E times psi j, where j is our index and it's going to go from 1 all the way to n. So unlike in 2.61, we are not given a very easily describable pattern for the H matrix that we can just extend to higher n values. Because remember, back in 2.61, we found a very easy pattern to follow, where it was just all the off diagonals were -1, and then we had like certain terms for the middle diagonals, and then everything else was 0. So realistically, we sort of expect our H matrix to follow the same sort of process, but in this case, it's not as easy to figure out what the actual pattern is. So because of that, the code is going to be made slightly harder in that we're going to have to brute force out our matrix by sort of shoving in this algorithm and finding it that way. So that is where the primary challenge of this problem is. Because once you find the actual H matrix, then the actual process of finding the eigenenergies and then also, you know, solving for the eigenvectors and then like plotting out psi, that becomes, you know, that's just the exact same steps you did in 2.61, but you're using different numbers for your matrix. So if you have the code back from 2.61, you literally just shove your new values into the code and you get your answers. The hard part, therefore, is actually finding the H matrix, and that's what we're going to do in Python. I'm only going to go up to that step because after that, everything else is the exact same as 2.61. I don't feel like it's worth it to go through all of it again. So because of that, I will cut and I will meet you on Python. Okay, welcome to Python. The first thing we're going to do is we're going to define the coefficient at the front of our matrix, which we saw earlier in the actual paint. It was the formula n plus 1 squared times h bar squared divided by 2ma squared. So I'm going to start by doing what I always do, which is importing everything from SymPy. So from SymPy, import star, which means just import everything from SymPy. Then I'm going to define my coefficient. So coefficient is equal to 11 squared, because remember it's n plus 1 squared, so I'm defining it as 11 squared, then multiplied by h bar squared, so I'm going to write that as symbols h squared. Because remember, Python cannot actually, or SymPy specifically, has to define variables this way, because otherwise it treats them as a call function. This is then divided by 2ma squared, so 2 times symbols m times symbols a squared. And then let's just print our coefficient. 121 h bar squared over 2ma squared. So we're not actually going to use this, or specifically I'm not going to use it because I'm not going to go the full way of the problem and solve for the actual eigenenergies. I'm just trying to obtain the matrix. But this is, for those of you who want to go the full way, this is your coefficient. You would just attach this to your actual matrix once you find the matrix. And now, let's actually sort of find our algorithm. So our algorithm is going to be in terms of psi. And we have the algorithm in terms of psi with subscripts. So when you're working with subscripts in SymPy, it's a little bit more complicated. I'm going to start by defining my subscript as a variable. So j is going to be defined as symbol j, like that. And what I'm going to do is my first goal is just to write out the base algorithm. So let's do that first. So algorithm, I'm going to call it algo. This is going to equal, so negative, right? It's going to be psi of j plus 1. So symbol, I'm going to call it p underscore, concatenated with the string value of j plus 1. So j is just a symbol j, and I'm going to add 1 to it, and I'm going to turn that into a string. So this is going to give me, I'll just show you. This is going to give me negative psi of j plus 1, which is our first term. Our second term is going to be the middle term, which is going to be a little bit more complicated, right? So plus, and then it's going to be 2 added with, and then that thing in the middle. So it's a bunch of variables. So it's like 500 divided by n plus 1 squared times sine of something. So first off, I'm going to just write out 500 divided by n plus 1 squared as a number. So I'm going to estimate it at 3 decimals, just 4.132, because this is going to be 500 divided by 11 squared. And then this is multiplied by sine of j times pi divided by n plus 1, which is 11. So I'm going to write this fully out without using the n index. I'm going to write it out with n actually being substituted as 10 in this case. So j multiplied by pi is just pi, written like that, and then divided by 11. And then this whole thing is multiplied by symbol psi underscore, this time it's just j. So if I write this out, now we have this term. So 4.132, this is 500 divided by 11 squared. And then sine of pi j divided by n plus 1, which is 11. And then we're adding 2 as well. And then finally, we're subtracting the symbol of psi underscore plus string, this time j minus 1 instead of j plus 1. If we write this out fully, we should have everything. So now that we have our algorithm, we can actually write out the matrix. So I will cut and go to that. Okay, finding the actual matrix. So we're going to define this in the same way that we did in 2.61, which is I'm going to start by writing out an empty list. I'm going to call matrix rows. Next, I'm going to say, okay, well, I know that j goes from 1 to 10. So I'm going to say for j in range 1 to 11. Because remember, range stops right before this integer at the end. So this is going to give me j equals 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Next, I'm going to define the individual rows of my matrix, because this is, in this case, since we're splitting into j equals 10, our matrix is going to be a 10 by 10. So I'm going to define individual row as equal to just 0, 0, 0, 4, 5, 6, 7, 8, 9, 10. Is that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? Yeah. Individual row, yep. Okay. Now, I'm going to rewrite my algorithm. Or I suppose I'm going to say I'm going to take this and I'm just going to shove it back. Because this was just, I wrote this up above just to give me an idea of what the algorithm's supposed to be like. I'm actually going to use it here. So negative symbol, psi of j plus 1 plus 2 plus blah, 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 blah. And then what I'm going to say is, okay, so remember the way this works. The coefficients in front of my psi terms are going to be what actually go into the matrix itself. And then we have one exception thing, which is that, you know, the first and last rows are not going to have sort of the first and last term. So just to show you what I mean by this, I'm going to print the algorithm in each case. So this is going to give me, you know, 10 equations, right? And what we see here is basically just like the respective coefficients for each individual term. So this first equation is going to give us coefficients for psi 0, psi 1, and psi 2. So these would respectively go into the matrix positions at, you know, 1, 0, 1, 1, and 1, 2. But in this case, because of our boundary conditions, remember, psi 0 and also psi 11 both have to equal 0 because of boundary conditions. So what this basically tells us is that in row 1, the first term is going to have the coefficient of 4.132 times sine of pi divided by 11 plus 2. And the second element in that row is going to be negative 1. So for row number 1, this term is going to get replaced by this coefficient, and then this term is going to get replaced by negative 1 because that's the coefficient from here. And then we move on to row 2, which is going to have negative 1 for, you know, index number 1, and then it's going to have this for, you know, the second term. It's going to have negative 1 for the third term. Everything else is going to be 0. Then we move on to the third row, which is going to be for, you know, the second, third, and the fourth elements, so on, so on, so on. So what we're basically trying to do is we're trying to, in this for loop, we're trying to basically just add each of these coefficients into the individual row and then add that as a list into matrix rows. With the exception that P0 and P11 both have to equal 0. These we don't care about, basically. We don't add them into our matrix. So to actually do that, what I'm going to say is if j, let's see, yeah, okay. So if j minus 2 is equal to 0, so remember, the matrix rows, the indexes are going from, you know, or sorry, if j minus 1 is equal to 0, so this is basically saying, you know, if we have P0, effectively, I'm going to pass. Otherwise, if it's not, then I'm going to change individual row. I'm going to change the j minus 2 element to equal negative 1, effectively. So what I'm basically doing is sort of the first element, sort of the j, where is it? Yeah, the j minus 1 element, the coefficient in front of it is always negative 1. And it's going to go into my matrix. But remember, the row indexes go from 0 to 9, whereas my j index goes from 1 to 11. So there's an offset of negative 1. So instead of j minus 1, I'm writing to j minus 2 instead to compensate for that offset in the index method. So that takes care of that. Next, individual row, and this is going to be just for j, so I'm going to add this as the coefficient. But remember, once again, there's an offset. The individual row indexes read from 0 to 9, and then the j index goes from 1 to 10. So because of that, there's an off index of -1. So instead of writing for j, I'm writing for j minus 1, and this is going to be equal to this coefficient right here. Next, if j plus 1 is equal to 11, so this is going to give me the edge case where we have psi 11, then I'm going to pass just like before. Otherwise, individual row, and this time, once again, because of the offset of -1 in the index method, instead of j plus 1, it's just going to be j. And this is going to be replaced with, and if I look at here, the coefficient in front for the j plus 1 term is always going to be -1, just like that. And then finally, I add the resulting row, matrix rows dot append individual row. So this is basically just changing all the respective coefficients to what they're supposed to be for that individual row, then adding it to the matrix row. And then finally, I'm going to say I'm going to turn this into a matrix. I'm going to use the matrix command. I'm going to turn matrix rows into a matrix. And if I do this, I should get a nice 10 by 10 matrix like that. So this is going to be the off-diagonal terms, and at this point, I am pretty much done, because I've found my H matrix. From here, if I want to find the energies, I would then use the eigenvalue problem that we did in 2.61. I would just repeat all the code, but I would define this new matrix. I would define it as, like, I would say, like, H matrix is equal to this, and then I would do all of the sort of stuff that I did back in 2.61 to get the eigenvalues, and then after that, if I wanted the eigenvector, I would do the exact same thing. The problem asks us to graph the wave function, so that's just basically you find the eigenvector, and then you recognize that the different values on the eigenvector are basically approximations for the wave function at that point, and you just plot it. And then you're pretty much done. So everything after this is the exact same as 2.61. I'm not going to bother with it. We are pretty much done with this problem.